Okay, well, the last example took us a little bit of time, but it is nothing that we hadn't done before other than adding the fact that we've got a set of linear factors. Well, what could we say if we're actually given one of the zeros of the polynomial? And we're going to use the complex pair theorem. It goes like this. We have a polynomial, and we know that a plus bi, where b is not equal to 0, is a complex zero of a polynomial function that has only real coefficients. Well, if that's the case, then the conjugate a minus bi must also be a complex zero of the polynomial function. So what's the implication? Well, let's look at our example. We've got p of x is this fourth degree awful looking polynomial, x to the fourth minus 8x cubed plus 46x squared minus 40x plus 205. We're given that 4 plus 5i is a 0 of p of x. Well, right away we can use that complex conjugate theorem because we're basically being told, not in so many words though, that x equals 4 plus 5i is a 0. Therefore, by the complex pair theorem, x equals 4 minus 5i must also be a 0. All right, and that's useful because in a way what we can do is we can use this to our advantage. We can take 4 minus 5i, and in the book what they do is they show a synthetic division using 4 minus 5i and 4 plus 5i into a polynomial kind of similar to this one, but I'm going to do something different with you. I always say, well, look, if x equals c is a 0, then we know that x minus c is a factor. And we've established this a few times now in our work through chapter 3. So how does this help me? Well, c is any complex number. Here is c1 for us, right? Here is c2. These are two complex numbers. So you can take these complex numbers and actually subtract the entire thing from x to make it a factor. So if x equals 4 plus 5i is a 0, then x minus 4 plus 5i is also a factor. Right, so we've got two factors here. We've got the factor x minus the quantity 4 plus 5i, and we'll have x minus the quantity 4 minus 5i. Now, I know how everybody loves multiplying polynomials, and this one's no different. I'm going to use my FOIL method. I'm going to take these leading coefficients, these leading x's right here, first terms. So I'm going to get x squared. X times x is x squared. Then I'm going to take x, and I'm going to multiply it by that quantity, 4 minus 5i. So I will have x minus x times 4 minus 5i. Remember, we're using the FOIL method here still. And then my inner terms, I'm going to have minus x times the quantity 4 plus 5i. Finally, I'm going to multiply my two last terms. It's a negative times a negative. That makes it a plus. 4 plus 5i being multiplied by 4 minus 5i. That's a 4 over here. There we go. 4 minus 5i. And you're looking at that and going, well, boy, that seems kind of long. But it's all right. It'll shorten up. Watch. X squared minus, distribute your x. So minus 4x plus 5i times x minus, distribute your x again, minus 4x minus x times positive 5, so that's minus 5ix. And then we have a little bit of complex multiplication to take place, but that's easy, right? Because we're going to have 16 minus 20i plus 20i, so middle terms will drop out, minus 25i squared. Well, our terms with I drop out. So we're left with x squared minus 4x minus 4x, so that's minus 8x. We have 16 minus 25i squared. Well, that's plus 25. So in fact, our expression becomes x squared minus 8x plus 41. So this is one of the factors of P of x. And we can get the other factors now by using long division. So let's do our long division here. And let's find out what should happen. In long division, x squared minus 8x plus 41 divides into x to the fourth minus 8x cubed plus 46x squared minus 40x plus 205. Those just seem like big numbers, but not as big as we could make them. So what do you have to multiply by x squared to get x to the fourth? That's right, it's got to be x squared. So x squared goes here. X squared times x squared gives me x to the fourth, just like I wanted. X squared times negative 8x gives me minus 8x cubed. 41 times x squared, so that's plus 41x squared. And we're going to subtract that entire expression away from the line above it, which means the x cubed term drops out, and now we're left with 46x squared minus 41x squared, so that's 5x squared, minus 40x plus 205. So let's try this with, what do we multiply here? Well, we're going to multiply by 5. So plus 5. 5 times x squared gives me 5x squared, just as I was hoping to get. 5 times negative 8x gives me minus 40x, again, as I was kind of hoping for. And 5 times 41, well, you better bet it's 205, right? So that when we subtract, we get 0 as our remainder. And so what we've just found is that our polynomial will also have x squared plus 5 as a factor. So that means P of x now has factors like x minus the quantity 4 plus 5i times x minus the quantity 4 minus 5i times x squared plus 5 with no remainder. Well, it shouldn't, it's a factor. And so our other zeros will be zeros of x squared plus 5. Where does that happen? Well, x squared plus 5 is equal to 0 whenever x squared is equal to negative 5, which is to say that our other two zeros look like they're going to be complex numbers as well, because this is plus or minus the square root of negative 5, which we know reduces as x equals plus or minus I times the square root of 5. So that's 2 more zeros right there for a total of 4 zeros. The fourth zero is fourth degree, right? So this is a complex zero of a polynomial function. In fact, we have 4 complex zeros, but we still have real coefficients. All right, more to come.